Hello, my name is Peter Colopy, and I work as the Radiation Safety Officer for Austin Master Services, an oil and gas waste handling firm that provides waste disposal and remediation services for oil and gas operations in Pennsylvania, West Virginia, and Ohio. Before we begin today's presentation, a few housekeeping items. This course is approximately 90 minutes in length, and because it's being presented in a computerized online training module, feel free to stop at any time to take a break. You'll be able to pick up where you left off just by clicking on the restart arrow. There are quiz questions embedded within the presentation that should be answered before proceeding to the next session. If you are doing this session as an individual user, your answers will be forwarded to me automatically upon completion of training. I'll create a grade score for the quiz, and I'll send back the marked up copy of the quiz, with some detail providing greater information on any question you may have missed. Where a question is multiple choice, there is only one correct answer. If you are taking this training as a group, you'll each need to complete those same quiz questions on a paper exam sheet. Scan the completed sheets into a PDF and email to me at either pcolopy@austinmasterservices.com or pncolopy@yahoo.com. The same grading and return system will be used for paper copy exams as for the online exams. There will be a follow-up live hands-on session for use of instruments and a demonstration showing how to perform effective surveys. The hands-on training will probably be provided by our Assistant Radiation Safety Officer, Troy Mazer. Also, this production is kind of a quickie given some time constraints and will be a bit rough, as I usually do a run-through or two to smooth out the edges. If you find that there are technically inaccurate portions, such as the details of what goes on during well pad development, or some parts just don't help you with your job, feel free to feed that info back to your management so they can pass along to me. After this first go-round, I'll be editing this training for future use, and your input will go a long way to making the training more effective for future users. Okay, so why are we even doing this training? CONSOL is required by our Department of Environmental Protection, Pennsylvania policy to develop what is called a radiological or radiation action plan for their well pad work activities. So you have to ask, why do you think the state requires an action plan? What are they actually trying to accomplish with this? We hope during this training to be able to answer those questions for you. Most of the action plan centers on the performance of surveys and the actions to be taken based on those surveys. However, there are specific training requirements that go beyond just instrument use and survey. This training will focus principally on radiological safety fundamentals, protective measures, and action plan requirements. As stated previously, there will be a follow-up hands-on demonstration for instrument use and survey. Shown here are the specific training requirements by the state. I'll try to make the fundamentals as digestible as possible, and I encourage you to send questions to me if for any reason I lost you during this presentation. If I get enough questions, I may request that we do a quick 10-minute conference call or an online Google meeting so I can specifically address your questions. The major take-homes for this training are: can you distinguish between contamination and radiation? Can you list the means by which you can limit exposure to radiation and radioactive contamination? What type of surveys are required by the action plan, and what actions do you take when an action level is exceeded? If you can get those three concepts down pat, you are good to go. One caution is that this training is geared to well development work, so some facets of the radiation hazards and survey methods for other parts of the oil and gas cycle will not apply. For example, if one is working downstream in, say, the gas compression and transport cycle, the mix of radionuclides and the method of survey are different than what is described in this training. The current CONSOL Radiological Action Plan is geared toward well development activities. This plan may be modified based upon any changes or additional activities that occur during generation and disposal of the radiological waste contaminants from oil and gas development and production work. A brief look at the likely waste materials generated during development activities are listed here. Vertical drilling and horizontal drilling produce radiological waste materials termed norm, and those cuttings are typically have minimal radiological contaminants. Filters and sludge from flowback and production water treatment have the potential for greatest contamination and are termed T-norm, or technologically enhanced naturally occurring radioactive material. We'll discuss what makes a waste material norm, or naturally occurring radioactive material, versus T-norm, and why we distinguish later in this presentation. So what should you take home for this training? What is radiation? How is it measured? What is the risk from exposure? If I want to minimize the risk from exposure, how do I do that? How do I perform a survey? What's a good number, and what's a number I need to act on? What are the responsibilities and requirements for me within the CONSOL radiation or radiological action plan? Here is a list of topics I'll cover when discussing radiological fundamentals. Most important to understand is the difference between radioactivity, radiation, and contamination. Once you understand the difference, all the steps to minimize exposure will begin to make sense. It is important to remember that the protons define the chemical nature of the atom. So an element with many isotopes, that is the same number of protons but different number of neutrons, will chemically behave the same. The nuclear properties make no difference in how the material is taken into the body or how it transports through the environment and chemically reacts with other chemicals in the soil and water. For this example, whether it's a radioactive or non-radioactive form of hydrogen, it will chemically behave the same as hydrogen. Here are three isotopes of hydrogen. The first is regular hydrogen with an atomic number of 1 and a mass of 1. The second is what is called a deuterium, and that basically has a neutron and a proton in the nucleus. And the third is hydrogen-3, otherwise known as tritium, and that has 2 neutrons and 1 proton. The superscript above the atomic symbol shows the total number of protons and total number of protons and neutrons and defines the mass of the nucleus. The subscript at the bottom of the symbol describes the number of protons and tells you chemically how the atom or element is likely to behave. For radioactive materials, there is an imbalance between neutrons and protons in the nucleus. That imbalance creates an energy state that by nature wants to be more stable. Consider when you spin a top, what is actually happening? In that case, you have taken mechanical energy, your effort to spin the top, and the top through frictional interactions loses its energy to the surrounding environment until all the energy is gone and it falls to the table surface in a stable state. By comparison, the same thing is happening in the nucleus, only the energy transfer is in the form of photons or particles ejected from the nucleus. That ejection causes the nucleus to try and rearrange itself into a more stable state. In almost all radioactive decays, a different element than a decaying parent results. For example, in the case of uranium-238, a naturally occurring radioactive material, which you will encounter in oil and gas work, and one of the heavier elements in nature, an alpha particle, which has a mass of 4 and a charge of 2, is emitted from the nucleus. The resulting element now has a mass that goes from 238 to 234 because it lost that mass of 4 through the alpha particle, with a total number of protons of 90. The resulting element is a different chemical, thorium-234, which is also radioactive but has different chemical properties than that of uranium. Those emissions from the nucleus shown in the previous slide are termed radiation. So listed on this side is the classic definition of radiation. Note that radiation, while typically associated with things nuclear, also applies to the transmission of energy through a medium, typically air. So heat and sound energy are also forms of radiation. But in their case, it's principally energy transfer via the vibration of the air molecules. For the purposes of our discussion today, we will talk mostly about electromagnetic radiation. Electromagnetic radiation contains an electric and a magnetic component to its waveform. In the nuclear world, we consider particles by extension to act like photons or light rays of radiation. So those particles or photons emitted from the nucleus during a radioactive decay are also considered forms of electromagnetic radiation. It's basically energy moving through air. When the energy interacts with a substance, it does so through a process called ionization. I included this slide to show that electromagnetic radiation is more than just nuclear-generated radiation. It includes light, microwaves, and even the radiation generated during power transmission. Radiation is a wave that has a specific frequency. If you were to look at the waves rolling into shore along the beach, for example, they have a length and they have a height, but they also have a frequency that determines how quickly they appear and the interval of the peak of each wave. Very high frequency waves, those with very short wavelength, are considered nuclear radiation. Note that the visible light that provides us sight is at the higher frequency end of the spectrum. Microwaves, such as those in communication dishes or in your microwave oven, have long wavelengths and low frequency. Finally, ELF, or extremely low frequency radiation, such as that from electric transmission lines, or 60 hertz, have wavelengths that are measured in miles. So here's a first principle. The process of ionization is essentially an energy transfer process from the electromagnetic radiation to the atom or molecule the radiation interacts with. Whatever is causing the ionization is transferring some or all of its energy to the ejected orbital electron. In turn, the ionized atom or molecule, because it is no longer electrically neutral, will interact with another atom or molecule in the vicinity. That next interaction is a chemical energy transfer process. So it's basically taking the energy transferred to the nucleus during a radioactive decay and turning it into chemical energy transfer. Your body naturally undergoes hundreds of thousands of these type of ionizations and chemical processes in the body every day. The body is well equipped for most individuals to utilize these energy transfers in a beneficial way, or repair them if they are not beneficial. Each of the different types of radiations emitted during radioactive decay can present different hazards based on their energy, mass, and charge. So we're going to talk about the three most common types of radiation emitted during a nuclear decay, of which all of these radiations are experienced or seen during oil and gas operations. The first are alpha particles, which have a relatively large mass and charge. Essentially, on a nuclear scale, their mass is 4 and their charge is a +2, compared to the other two types of radiation. Beta radiation, which is basically an electron, has a very low mass and a charge of a -1. And gamma rays or photons have no charge or no mass. It is the charge and mass properties which determine how efficiently the energy from the radiation is transferred to the surrounding media, such as your body cells. This energy transfer, as described previously, will then cause chemical interactions with the interactive media. If it's a media such as a piece of wood, it's no big deal, as the wood is inanimate. For living cells, there is the potential for damage to be done to the DNA. Knowing the type of properties helps in deciding what protective measures one takes when handling radioactive materials that are emitting these radiations. Alpha particles are not very penetrating and cannot travel more than several centimeters in air. Consequently, radioactive material emitting alpha particles and external to the body are not a hazard because the alpha particle energy is easily dissipated in air, and an alpha particle cannot penetrate the clothing or the dead layer of the skin that surrounds the human body. For beta particles, because they are a lower mass and still have a charge, they're less likely to interact with the air than an alpha particle, and thus can travel from a few centimeters to several meters in air. Their travel length in air is dependent on the beta energy. In the case of oil and gas radionuclides that decay by beta emission, the beta particle can travel a full meter in air. However, the particle has a high interaction probability when traveling through denser material, such as normal PPE and safety glasses, and that will absorb all the beta energy. So a beta particle can be a skin and eye hazard if those portions of the body remain unprotected. If radioactive material is ingested or inhaled into the body, then the hazard becomes more significant for beta and alpha emitting radionuclides. This is because transport in the body will be dependent on the chemical nature of the radioactive material. Once the radioactive material is incorporated into the cells of the body, any emission of beta or alpha particles will result in the live cells absorbing the energy of those emissions. Gamma rays or photons have no charge or mass, and consequently, they have a low probability of interacting with the media they travel through. The probability increases with the density of the medium, such that lead ends up being a very good shield for eliminating gamma rays because of the high probability of interaction. Gamma rays are principally an external hazard, but it should be remembered, because of their penetrating capability, they can deposit their energy in the skin, the bones, and the organs of the body. While gamma rays from radionuclides that have been ingested or inhaled into the body will contribute to the internal dose, their contribution is minor compared to the alpha or beta particle energy contribution when that radionuclide emitting alpha or beta particles is inside the body. In summary, radionuclides emitting gamma rays pose an external hazard to the body. Radionuclides emitting beta and alpha particles can be a hazard if the radioactive material is ingested and the live cells within the body are exposed to the radiation emitted by those radionuclides. In oil and gas, you have radionuclides emitting all three types of radiation. So handling oil and gas waste materials poses both an external as well as an internal radiation exposure hazard. One characteristic of a radioactive isotope is they have unique half-lives. That is, the rate of decay is different for each type of radionuclide because the time in which the nucleus is making transitions to become stable by emitting radiation is based upon its specific neutron to proton type of imbalance. As shown in this illustration, a half-life is the time it takes for 1/2 of the population of radioactive atoms of the same type to undergo a decay to a more stable state. It's basically a halving principle, such that a very large population of radioactive atoms never really becomes completely stable. Theoretically, there will always be some radioactivity left. A good analogy is Aristotle's theorem of the half walk, where one walks half the distance to a point, then walks another half to the remaining distance. Theoretically, you can never arrive at the destination point as there's always an incremental distance left. In the examples shown here on the slide, if I have a half-life of a nondescript half-life of 100 atoms, after one half-life, that 100 atoms, 50 decay, and 50 radioactive atoms remain. When another half-life goes past, those 50 atoms, 25 decay, and 25 remain. When another half-life goes back, I have approximately 12 atoms have decayed and 12 atoms remain. So that's basically an illustration of the halving principle for half-life. As you will see shortly, oil and gas radionuclides cover a wide range of half-lives, with some in the billions of years and some as short as a minute. For practical purposes and well development work, the radionuclides do not decay away and are always present. To aid in radiological safety decision making, we use a term called the REM, or in System International units, the sievert. The REM is often referred to as a potential biological damage, which we will discuss further in the slides on biological effects of exposure to ionizing radiation. In the case of the REM or sievert, it doesn't matter whether the energy transfer was from interaction with alpha particles, beta particles, gamma rays. The potential biological risk is the same. Think of the famed quote from Shakespeare's Romeo and Juliet. What's in a name? That which we call a rose, but another name would smell as sweet. In the case of radiation, a REM is always a REM regardless of the type of radiation. To give you some perspective on that, background radiation levels of 3 to 12 micro-REM, which are approximately a millionth of a REM, are typical of those areas in the United States. For oil and gas waste, exposure rates will range from 10 to 30 micro-REM above background. Because radioactivity is a property of the atom, we need a way to quantify how much of that property is present. We do so by looking at how many nuclear transitions occur per unit of time within a population of radioactive atoms. Remember, a radioactive isotope wants to emit radiation to restore an energy balance to the nucleus. This process of restoring the balance is a probabilistic process, meaning that the time for a decay or nuclear transition of a radionuclide is not a set time, but rather one that can be described by looking at the rate of those decays in a large population of radioactive atoms. The original unit used to describe the rate was called the Curie, which is essentially 37 billion nuclear transitions or decays per second. Seems like a lot, but one also needs to know the type of emission to determine just how hazardous the radioactivity may be. For example, tritium, the radioisotope that I showed you in the earlier slides, decays by an extremely low energy beta emission, and it's thousands of times less hazardous than the same amount of radium-226. So just knowing the activity is not enough to determine the hazard. You need to also know the type of radiation emissions and the energy of those emissions. The System International unit, which is the unit that is used by just about everybody at the United States, is called the becquerel, as opposed to the Curie. And a becquerel is simply one disintegration or decay per second. The reason we include it here in this presentation is that in the shipping of radioactive materials, the Department of Transportation requires that System International units be included somewhere on the shipping papers. But for most of what we're going to do, we're going to stick to the English units. And you're going to hear us refer to picocuries, which is the basic number that you see in background levels of radioactivity in soil and essentially what you'll see in oil and gas generated waste. Because during the Earth's formation, radioactive material was created, we have what we call naturally occurring radioactive materials present in the Earth's surface. So one is always exposed to radiation from those naturally occurring radioactive materials. In building materials and soils, we have uranium and thorium. In our body, we have potassium, of which one isotope of potassium, potassium-40, is radioactive. So one will always be exposed to radioactivity and radiation in everyday life. We tend to think the exposures to those naturally occurring radionuclides and radiation as background. Most naturally occurring radionuclides exist in concentrations of 0.3 to 3 picocuries per gram. So the amount of radioactivity in normal soil is quite low. Here are some units that we use to describe radioactivity and contamination. We use the picocurie per liter to describe the amount of radioactivity in a volume of water. We use picocuries per gram to describe the amount of radioactivity in a solid. And we use dpm per area to describe the level of contamination on a surface. When we discuss instrument use, we'll describe further why we use the term dpm rather than picocuries to describe surface contamination. However, the term dpm, like picocuries, is still describing the number of nuclear disintegrations. So with a bit of unit conversion, they are basically the same unit. It's kind of like describing speed in feet per second and then converting to miles per hour. So here's a brief listing of radionuclides likely to be encountered during well development and production processes. The levels are highly dependent on what shale formation one is drilling into, and also varies greatly over a wide area of the same shale formation. Note the lower concentration of radium-228 than radium-226. This becomes important when looking at the shipping of these materials and trying to determine if they meet DOT classification as a hazmat material. And we'll have more on that later when we talk about surveys for the purposes of DOT shipments. Before we begin a more detailed discussion on oil and gas radionuclides, let's talk about equilibrium. Oil and gas radionuclides are called chain radionuclides. That is, when one decays, the resulting transformation is another radionuclide, chemically different but still radioactive. Because there are hundreds of thousands of these radionuclides present, the chain is always decaying from one radionuclide to another. The illustration here is meant to help visualize that process of one radionuclide transforming, or in the case of dominoes, tipping over, and then the next domino transforms immediately after the one preceding it. We call this phenomenon equilibrium. It's important because all the radionuclides within the chain are at an equivalent level of radioactivity when under equilibrium. Meaning, if you know the amount of one radionuclide, you thus know the amount of each radionuclide within the chain. Here is the first of what are called chain radionuclides. The head of the chain, uranium-238, decays through thorium-232, protactinium-234, uranium-234, and eventually decays to radium-226, which is one of the principal radionuclides that we see in oil and gas. Here is the first of what are called chain radionuclide series. The parent or head of the chain illustrated here is uranium-238, a naturally occurring radionuclide. That is a radionuclide that has been here since the Earth's formation. The radioactive parent decays to a daughter or a progeny, and that daughter or progeny then decays to another radionuclide, and so on. And as I described before, I talked about equilibrium. That is, after a long enough time period, every time U-238 decays, there's also a thorium-234 decay, followed by a protactinium-234, and so on down the chain all the way down to polonium-210 until stable lead-206 is formed. So when in equilibrium, if I have a certain amount of radium-226 in equilibrium, I have the same amount of radioactivity of uranium-238 at the top of the chain. Here is the second most important chain that we'll find in oil and gas radionuclides, and that's headed by thorium-232. And notice that it also decays to a radionuclide that is radium, or this is radium-228, which has a much lower half-life, 5.8 years, versus the 1600 years for radium-226. But essentially the same decay process occurs as with U-238. But the key in both of these decay chains is the radium. Radium is typically more soluble than the thorium or the uranium parents, and as such, they will be removed from the shale formation during hydrofracturing, which is why that you'll see large amounts of radium in sludge and in filters, but you'll see very limited amounts of uranium and thorium. Okay, so let's talk about norm versus T-norm. The fundamental difference between norm and T-norm is the process which produces it. T-norm type materials are materials which are naturally occurring, but because of the nature of the process, the concentration of the radioactive material has been enhanced. So a classic example is when one hydrofractures the shale, they take the radium that's in the shale, which is somewhat diluted because we have more than just radium in the shale, and it gets reconcentrated as it's pulled out in a sludge form, and therefore I've created more radium per gram of weight in the sludge than I would have if I simply took the shale out of the ground and counted the amount of radium in it. So I've technologically enhanced the concentration of the radium in the sludge. So we call that T-norm. On the other hand, for something like drill cuttings, the naturally occurring radioactive material pretty much stays in its natural concentration. That is, I drill in, I pull the drill cuttings up, I haven't changed the concentrations of the radioactivity by a significant degree in the drill cutting. So we call those norm as opposed to T-norm. And in some states, there's a difference for the two and that difference allows you to do certain types of disposal for norm that you can't do with T-norm. In almost all cases for oil and gas waste materials, the T-norm radioactivity levels are higher than the norm. For oil and gas, the T-norm waste will have large concentrations of radium-226 and radium-228 and minimal concentrations of uranium-238 and thorium-232. Norm waste will have approximately equal levels of U-238 and radium-226 because they're in the same chain, and they'll have approximately equal levels of thorium-232 and radium-228 because they're in the same chain. So let's get to some major concepts here of radiation and radioactivity, which provide the basis for why we do radiation protection the way we do it. So a major concept behind radiation protection is the distinction between radiation, radioactivity, and contamination. As previously stated, radiation is the photons or particles emitted from radioactive materials. Radioactive materials are simply elements or atoms whose nuclear properties include an unstable nucleus that will emit radiation and become stable. If one has radioactive materials in a place where it is contained, then one is exposed only to the radiation emissions that can penetrate beyond the container walls. However, if the containment is lost and radioactive material is spilled to the environment or onto a person's skin or clothes, then we call that contamination. One can then breathe or ingest the radioactive contaminants. In addition, if the material is not removed from the clothing or the skin of the body, then one can take the contamination with them, and they are continually irradiated by the contaminants that are on their clothing or skin, and in addition, potentially will ingest or inhale those contaminants later on. So contamination, simply put, is simply radioactivity where we don't want it. So let's next discuss potential biological effects from exposure to ionizing radiation and radioactive materials. To do that, we need to provide some perspective on how much is a lot and how much is small. Each individual in the United States, on average, receives a dose of 620 millirem or 620,000 microrem in a year. Medical-related exposures account for half of that annual dose. Typically, medical exposures include X-rays, nuclear medicine scans, and more recently, CT scans. Background doses come from cosmic radiation, which is the radiation emanating from outer space and reaching the Earth, naturally occurring radioactivity materials in the soil and building materials, and from radioactive materials that make up part of the human body. Radon accounts for 2/3 of the exposure to naturally occurring radioactive materials. If one never goes near an X-ray or does a nuclear medicine scan, then the individual's dose will be well below the 620 millirem. On the other hand, significant trips to get CAT scans will put one well above the 620 millirem. So it's important to remember the 620 is an average number and not the actual number that every person receives. Some people receive more and some people receive less. But in general, you can be pretty much assured, even if you're not receiving any medical exposure, you're getting around 300 millirem in a year. It is interesting to note that there are places in India, Brazil, and Iran where the local population receives background radiation doses well in excess of 1,000 millirem. mostly due to the fact that there are higher concentrations of thorium and uranium in the soils in certain areas of those countries. So given that, we are always exposed to ionizing radiation. So what's the concern? We know that at extremely high exposures, such as those from the atomic bombings of Nagasaki and Hiroshima, as well as other incidents of extremely high exposure, we see an increase in cancers within the exposed population. Note that these exposures are 10,000 times higher than what one would experience in oil and gas. Our problem is that we can't predict with absolute certainty that no effect is occurring at extremely low doses. So we assume there may be some effect, albeit extremely low. So by assuming the possibility a cell is experiencing a change in the DNA, then that cell may fail to repair, and the change will then lead for the cell to reproduce uncontrollably. And when cells reproduce uncontrollably, we call that cancer. And so the major harmful detriment that we're worried about by exposure to ionizing radiation is an impact on the cell, a change in the DNA, and a subsequent uncontrollable cell that divides uncontrollably and forms a cancerous tissue. There are a lot of barriers to that cancer potential occurring, but in the rad protection world, we take the prudent approach and assume it might happen. That it might happen is a very low probability. For example, as shown in this slide, one would need a relatively large dose of 10 rem or 10,000 millirem or 10 million microrem to cause 100 exposed individuals to incur a theoretical risk of a 2% increase in their cancer. Note that the cancer risk in a normal population is 42%. So we're talking about changing that population from 42 to 44 with a fairly significant radiation dose of 10,000 millirem. This is another slide illustrating the point made in the previous slide. The filled in dots are the naturally occurring cancer risk, and that little star represents the potential increased cancer risk if one gets exposed to that 10,000 millirem. So this particular risk report comes from the Biological Effects of Ionizing Radiation report authored by the U.S. National Academy of Sciences and is based upon the current epidemiological evidence that the risk of cancer proceeds in a linear fashion at lower doses without a threshold, and that the smallest dose has the potential to cause a small increase in risk to humans. The following illustration from the Beer report helps explain the relative risk of cancer to an exposed population. In this example, if we assume for a population of 100 people, we know on average 42, as shown by the darkened circles, will develop cancer sometime during their lifetime. If we expose all 100 to 100 millisieverts, or 10 rem or 10,000 millirem, from a radiation source, the total risk will increase by one person, or approximately 2%, as shown by that one star. If we assume the risk is stochastic or proportional to the dose, then an individual exposed to, let's say, 100 millirem, which is approximately 1,000 times less than that 10,000 millirem, 100 times less than that 10,000 millirem, the risk would then be 0.02%, meaning that the star is now reduced by a factor of 100, or essentially not seen. So as the doses get lower, the theoretical chance of a cancer begins to approach zero and is basically negligible. The caveat to all this is the problem of applying risk factors to large populations exposed to extremely low levels of ionizing radiation. The mathematics work, but the biological plausibility is not real strong. We do not see increased cancer risks in populations that have high background radiation exposures. So we suspect that the body's repair mechanisms play a role in cancer induction from exposure to radiation, and the body has a way of taking radioprotective actions at very low doses of exposure to radiation. We can't prove it, so we deem it prudent to assume that there is some risk, vanishingly small, at low doses, and so we strive to limit all radiation exposures. So what are the hazards? Principally, the first one is direct exposure from concentrated materials in containers. And that's exposure related to the gamma rays or photons that are emitted from the radionuclides that are contained in a container, in a filter, possibly in a drill mechanism, or in a bucket. All of those will be emitting photons, and because the photons are not charged or have a mass, they will travel farther, and sticking around that area, you will get exposed to those gamma rays and will have a direct radiation exposure. Second, risk is from the inhalation of airborne dust containing radium. And the third is the inhalation of radon. And the reason radon is different than the inhalation of airborne dust is because radon is an inert gas. So when radon gets formed as part of the radioactive decay of uranium-238 to radium-226 down through radium-222, it's an inert gas and it will not chemically react. So it basically diffuses up out of the ground and into the atmosphere. So if it's outdoors, it's not likely to cause much of a dose because the radon and the resulting progeny or decay products that come from the radon are swept away by the air, and there's limited time for you to breathe it into your lungs. However, if you're indoors with very, very little ventilation, there is a chance that the radon will build up to a level where the radon and its progeny will deposit significant energy to the live cells within the lung. So in oil and gas, with proper procedures taken, we have found that the dose is not likely to exceed 25 millirem or 25,000 microrem. In fact, most people never get a measurable dose, and we believe the dose is probably more around 5 millirem. But we like to use the upper limit just to give people perspective on what the highest doses are likely to see. One needs to compare that to the work limit, where those of us who work in the nuclear industry can receive up to 5,000 millirem in a year. And then there's a public dose limit of 100 millirem per year. At 500 millirem, we would require monitoring. So the dose that you're likely to see if the proper precautions are taken in oil and gas are much less than any of the regulatory values that we would have to implement in another radiation hazard environment. Okay, so let's talk about the protection measures you can take. We have a principle called the LARA. And so even if your radiation exposures are very, very low, we want to make your exposures as low as reasonably achievable. And we do that because we can't say for certain there is no effect. So it seems prudent to simply make everybody's dose as low as possible. So you'll find the protection measures that we're going to describe are fairly easy to employ and will also prove useful for exposure to other non-radiological contaminants. So much like your speed on a car, time becomes really important. So the less time you spend in an area, the less dose you're going to get, because if you multiply that exposure rate times time, that determines your external dose rate that you receive. So for the most part, exposure rate is given as a time, so it's a critical parameter. Some simple things to do to reduce your time in an area. Note where the low and high radiation exposure rates are in the area. So for example, if you've got a container of sludge or waste materials that you know is high, and you need to talk with somebody about planning a job, don't do it right next to the drum. Do it far away from it. If you're not working any place in the area, then stay in a low spot. If you have to be in a work area, stay in the lowest radiation dose rate spot that's there. Plan your task prior to entering the area, because the faster you do the task, the less dose you're going to receive. Make sure you have all the necessary tools before entering the area. There's no sense going back in and out to get tools. It's much better to just go in, do the job, and get out. Don't loiter in the radiological area. Do the job right the first time. Perform as much work as you can outside the area as possible. So where you can do things where you're putting something together or you're unpackaging something, do it outside of the area so you're not next to the source of the radiation. Even in high spots of radiation, don't rush, as the chances of any really high exposure or any issue happening is not very great. And so you're better off doing your job right the first time than having to repeat it and picking up a second radiation exposure that was unnecessary. The second method of protecting yourself is via distance. And in the immortal words of the talking heads, you may have to ask yourself, why does it seem brighter when I'm closer to a lamp in my house? It kind of seems obvious. We simply see more light rays emanating from the bulb. Well, the reason for that is light spreads out, and it's the number of those light photons of energy crossing paths with your eyes. So as you back away from that lamp, you have fewer light rays that are passing through your eyes, embedding on your retina, and therefore seeing more light. So things get darker as you move away from the light source. The same is true of radiation. If I have a radiation source, the farther I'm away from it, the faster that radiation dose falls. So we basically have a formula called the inverse square law whereas you double your distance from a source, the dose rate typically will drop off by the square of that doubling. So if I were at a distance of 2 feet from a source and I move back to 4 feet or another 2 feet, I actually decrease my dose by another square of that distance, or another factor of 4, as opposed to just moving back by 2. For oil and gas work, for our practical purposes, if you've got large quantities of material that's spread out all over the place, the dose rate will probably drop off linearly. That is, as you move back a foot, it'll drop off about the same distance that as you keep moving back linearly. So the inverse square law is important in the sense that if you need to be in the area but you don't need to be right next to the source, the farther are you away from the source, the less amount of radiation you're going to be exposed. Shielding, which is usually part of what we do in radiation protection, is not particularly useful, is of limited value in oil and gas work. And the reason for this is because of the low concentrations relative to what we see in other types of radiological activities, such as nuclear power or in nuclear medicine work, where the radioactivity concentrations are orders of magnitude higher than those you see in oil and gas. And the fact that most radionuclide wastes are dispersed. That is, they're large volumes, and it's very difficult to shield large volumes. So the shielding benefit that you're going to see most of the time is basically because the material's in containers and the radiation does not penetrate outside the container if it's alpha or beta, and the container walls will also absorb some of the gamma rays being emitted by the waste materials in the container. So we wouldn't recommend shielding being a great deal of time. However, I will say that if you've got a truck or some piece of equipment that's not radioactive between you and a container that has radioactivity, you're going to get some shielding and some benefit. So preventing inhalation and ingestion, pretty simple. It's a basic industrial hygiene function. Don't get dirt on you, don't eat the dirt, and limit the amount of dirt you can possibly inhale or ingest. So in a very wet environment, airborne levels for radioactivity are extremely low because the dust or mud containing materials simply don't go airborne. Now with radon, as I mentioned before, it's a bit different because it's an inert gas. In an outdoor environment, normal winds will sweep away the radon and the radon progeny, so dose to the lungs is very limited. In an indoor environment with limited ventilation, that is not the case. So the parallel to that is that imagine a large traffic tunnel like the Fort Pitt Tunnel. If the traffic is moving freely, the carbon monoxide exhaust has limited time to build up. If all the traffic slows down and is idling in the tunnel, the CO, or carbon monoxide, can build up to hazardous levels, thus the reason for the fans in the traffic tunnels. The same is true of radon. If you're in an enclosed space with lots of radium waste, there is a potential for significant radon exposures. Not a likely event during well development, but worth remembering if doing confined space work. Normally I would hand out the plan at this point, but because we're doing this as an online training, I'm going to have management provide you with a copy of the facility radiation or radiological action plan. Because this plan is currently a draft and under state review, there may be some minor changes after the state reviews and comments on the plan. But the plan basically has action levels, the required surveys, designated storage areas, signage and postings, and disposition of waste material. So let's discuss the action plan relative to well pad operations. I'll be the first to admit I have minimal expertise on well pad operations, so I've tried to keep this portion of the discussion to a minimalist view. As noted previously, the range of radionuclides and levels will change based on where one is in the oil and gas cycle. For well development, the least concentrations of radium will accumulate, and the corresponding exposure rates and levels of radioactivity will be less than where one has an actively functioning production well. Within this plan, there are basically three types of survey requirements. The first is for transport containers, incoming and outgoing. The second is for Department of Transportation surveys, and I'll talk a little bit about that later. And the third is for process facilities and equipment. So for transport containers, DOT would be the outgoing transport container if the material has enough radioactivity in it where it would meet the DOT hazmat level requirement, and I'm going to define that in a later slide. Because we are providing hands-on training, I'm going to do a brief overview of the surveys, and the person conducting the hands-on will fill in with more detail as to how you do the surveys and why you do the surveys and what the actions are when you reach a certain action level. So this will basically be a brief overview in the next several slides. Okay, background changes by both geographical location, but also by what's going on around you. Say lots of buildings made up of brick or concrete. So you'll need to establish background so you have an idea for your well pad what background is. This is normally done in an open field near the site, but where there's no containers of any radioactivity and no equipment. For an incoming container, you usually expect it to be radiologically clean. You need to look for clumps of debris and monitor that debris within several inches. You should reject it at greater than 10 microar per hour above background. But your management may want to accept that material. If you do that, remember, you are now handling a contaminated container, so take appropriate measures to keep the contamination from spreading off of the container. For outgoing containers, the outside should not have junk dripping from its sides. So essentially, the exterior of the container should be pretty clean. It shouldn't be a mess where you've got material floating down the outsides, because all that material is potentially contaminants that someone could get in contact with during shipment. If at 1 foot, the exposure rate at the outside of the transport container is less than 10 microar per hour, the container can probably go into a Pennsylvania landfill, as it will not set off the portal monitor. We use a rough rule of thumb of 3 picocuries per gram of radium for every microar per hour above background. So for example, if you had a background rate of 8 microar per hour at your site, and your exposure rate at 1 foot from the container was 100 microar per hour, then the net exposure rate would be 92 microar per hour, or 100 minus 8. And it is estimated that the radium content in this container is now 276 picocuries per gram, or 3 times that 92. This value would indicate that the shipment should go as DOT classified hazardous material, and you would need shipping papers, placards, markings, and labels. Those DOT shipping requirements are for another course. We're only going to cover the survey requirements here. In almost all cases, your waste materials will leave the site as DOT exempt, and thus a DOT type survey will not be required. But it's still important to remember that as you get high exposure rates, particularly above greater than 90 microar per hour above background, you may be running into DOT requirements, and you shouldn't be shipping this off without having a DOT qualified person look at the container and the shipping papers or bill of lading for the ship. So now, if you are 10 microar per hour or greater, shipping the waste to a Pennsylvania landfill becomes problematic, and you'll need to get an analytical sample or use my estimation scheme. Disposal in Pennsylvania landfills is a bit complicated, but essentially is limited by the combination of the volume and the amount of radioactivity within that volume. So you could have a high activity waste but a low volume, and the landfill may accept it. On the other hand, you could have a low activity waste, but the volume may be too high for them to accept. Only the person designated by your company for dealing with the landfill will be able to handle that aspect of it. So the way we've written the action plan is when you start to get over the 10 microar per hour background, you want somebody else stepping in and doing an assessment of that shipment before it goes out of the site. If you have to ship as a DOT hazmat material, you need to perform a survey of the container. The type of survey depends on whether the shipment is exclusive use, meaning the container is transported directly to the disposal or waste processing facility, or not exclusive use, meaning one can stop and pick up other containers between your location and the final destination. You essentially take a survey in the cab of the truck, ensuring the exposure rate is less than 2,000 microar per hour. You also take a survey at contact with the truck and at 2 meters from the surface of the truck, and you do that at several locations. Don't worry, you'll never in well development work exceed the DOT exposure rate limits, but the survey is still needed to prove that you didn't exceed it. You'll also have to take a contamination survey, which again, the hands-on trainer will provide more detail. Plus, we'll generate an instruction set separate from the plan that will show you how to go about doing the survey and how to record your results. Right now, the plan we have written has you taking periodic surveys of equipment and facilities. That could change when only surveys of material leaving the site need to be performed, and we'll be deciding that based upon comments from the state and what CONSOL management wants to do. But for now, we do have surveys being taken quarterly for some equipment and facilities. You should always make sure that any equipment or vehicle leaving the site are free of visible debris that may be radiologically contaminated. The surface contamination limits for radium are extremely low, and the guidance from which they were derived are a bit antiquated. So I hope to convince the state to use the more modern and up-to-date numbers. And those numbers will be reflected in the operating procedure that we give you for doing contamination surveys. The one important thing to note is if you start getting tanks or containers with exposure rates greater than 2,000 microarc per hour, you'll need to post them as a radiation area. Okay, so management of the plan. The plan has a couple requirements that both involve you as the surveyor and the worker, and some as the manager of the plan. There's an annual review that must be done. One has to submit any plan changes to the state. You'll have to ensure instruments are calibrated annually. You'll have to ensure the instruments are functionally checked before use, and I'm going to talk a little bit about that in the next couple slides. You need to maintain records of surveys and disposition actions, and you need to ensure that workers are trained. And that's fundamentally what's required in the plan. So for instrument operation, you're going to end up using two instruments for performing surveys. One is an exposure rate meter. They're pretty simple to use. The other is a contamination monitor. So the exposure rate meter is shown on the left, and the contamination monitor is shown on the right. That particular monitor on the right will be connected to a meter, and that meter will give you the output for whatever that detector is seeing in terms of contamination. Handling the contamination monitor is a bit trickier than handling the exposure rate monitor, which is one of the reasons why we want to do the hands-on training, because it really helps to have somebody show you how to do it. Then you do it, and that person's able to watch you do it and provide some guidance on the best way in which to handle the meter. So each day, you'll perform the following steps prior to instrument use. You'll inspect the instrument for damage, so any problems such as a cut cord that could render the instrument inoperable are identified before trying to use the instrument and repairs made. You need to make sure the instrument is within its calibration due date. On every instrument, there'll be a sticker that lists the calibration date and the calibration due date. And you need to make sure you're within that due date. And if you're not, you need to set the instrument aside and get another one that has a current calibration. You need to perform a battery check. It's typically a switch right on the instrument, and it's an easy check to perform. You need to then perform a high voltage check. You may have a good battery, but if there's a significant battery loss where you're hovering down at the lower edge of the battery check, this may cause the instrument to underestimate what is actually being measured, hence the reason for the battery check, or for the high voltage check. In some cases, the instrument, all you do is a battery check, and there's no high voltage check. And again, when you do the hands-on training, we'll go over that with each instrument with you. You need to perform a background check. That is, you want to detect what would normally be considered part of the background to make sure that your instrument is actually seeing background. If it's too high, the instrument detector may be contaminated, or you may have a source in the area you're doing the check in. If it's too low, the instrument may have an internal problem, and you're now failing to measure accurately the radiation in the background, and thus you may fail to measure the radiation from a source accurately also. Finally, a functional check, where you check to make sure the instrument can actually detect radiation above background levels. This functional check is done with a check source that has known amounts of radiation emanating from the source. You basically place it up against the detector, and you expect the radiation reading to be the same every day. And again, as I spoke earlier, we'll be going over that during the hands-on demonstration. There are a number of forms you'll need to track your survey info with. So that's one area where a change in the plan may change the nature of the forms. The instructor doing hands-on training is going to go over all the forms for you, but there'll be a daily instrument check form, there'll be an equipment survey log, and there'll be a truck survey log, and there'll be a detailed survey log when you start to get any of those action level exceedances. This is just an illustration of what those check sources will look like. You'll need to use those to perform the functional check. Whatever you do, don't lose those sources. They're not particularly high level. They're not a real radiological hazard, but you really don't want the radioactivity floating around in the ether because it's uncontrolled, and you'd really like to have all your radioactive sources controlled. Okay, performing a survey. So here are some generic steps for a direct radiation survey. Again, you'll get more detail from the hands-on instructor. You start by placing the meter on its lowest scale. You approach the equipment or the container you want to observe and observe the meter. As the meter responds, and if it starts to go to the point where it takes the needle and pegs it on the scale you're on, you then have to turn upscale so you can get a better accurate reading. You want to hold it at waist high for a circumferential survey, and typically we usually hold them at 1 foot from the surface. Now there's some surveys you're going to do on contact, and so that's simply a matter of holding the meter against it. Typically when we do a survey, particularly of like a truck container, we do what's called an S survey. That is, you hold the meter, you're right next to the container, and you move in an S pattern from left to right along the surface of the container, looking for the highest exposure rate that you can find. And you slow down as you start to see things, and you speed up when things seem to be about the same. And again, we're going to give you some hands-on work, and hopefully at the point we show up to do that work, you'll actually have some radioactivity there, which will make it a heck of a lot easier to demonstrate how to do the survey. Okay, postings and barriers. Typically, this is how we post. We use yellow and magenta rope. We hang a caution radiation area sign. We post so that anyone entering from any side can view the warning, and we post at a location where exposure rates are less than 2,000 microarc per hour. You don't need to be quite so formal. What's important is that people entering the area can see the radiation area sign and know, no matter which way they're entering the area, that they're actually entering a radiation area, so that they either avoid going into the area because they don't belong there, or they'll minimize their time in the area because they now know it's higher than what normally one would experience at the well pit. Okay, so we're done. So well development, in summary, has really low levels of radioactivity. You're going to use time, distance, and cleanliness controls to limit your exposure, and you're going to take and document surveys. And again, I can't emphasize enough, if you have questions or you feel there's things that weren't covered in this training, please feel free to get back in touch with me, because it will help me design and edit and revise this training for future users. Thank you and good luck.